Alright, hi everyone, welcome to my YouTube channel, City of Electrons. So in this video, we are going to do this, the integral form of Maxwell's equation. So our previous videos, and in the previous video, we did the differential form, which is the points form of Maxwell's equation. So we've handled all four equations in differential form. This video we are going to handle the four equations again, but in integral form. Now, so for Gauss's law of electric field, now note that this time sometimes it's just called Gauss's law. Okay, sometimes it's just called Gauss's law, but I like to add this electric field because this law is specifically for electric field. Okay, and this law shows the equation that comes out of this law. It shows for electric field. Okay, or it shows electric field. Like, I hope you get the point. Okay, leave comment in the comment section. Okay, now the total electric flux through a closed surface equals the enclosed charge. See, if you've watched the previous videos, you understand what we mean by total electric. You understand what we mean by electric flux, and then what the integral form means, what the differential form means. We've also explained that differential form is just for a point, integral form is for the total. Okay, so total electric flux. Now electric flux is written as this, right? Electric flux. Now they are saying that the total electric flux, when we say total electric flux, okay, through a closed surface, through a closed what? Surface, that means total has to do with something of integral. Okay, so it's through a closed surface, right? Through a closed surface, so that means this should be a what? A surface integral, and the surface is what? Closed. So we have this closed. That thing should be closed though. Telling me that it's a closed surface. Are we seeing it now? So now this thing, we are integrating it with respect to what? The surface area, A, surface area. Okay, if you check some textbooks, you will see this is what you see. This is what you see. DS. It's still correct. Okay. So, but let's just work with this dA. Now, so we have expressed this part mathematically. Okay, we've expressed this part mathematically. Total electric flux, total, we have the integral sign. Electric flux, we have this D. Okay, closed surface, surface in close, and the surface integral. Change with respect to what? Sorry, we are taking this integral of the surface area. That's why I have A, surface area. Okay, now equals to what? Equals to what? Equals the enclosed charge. An enclosed charge is written as this: charge enclosed. Are we seeing it? Charge enclosed or enclosed charge. But recall that this equals what? This. We've said this in the previous video, so please check it out. Okay, all the videos are linked. It's one class, all the videos are linked. So from this, substitute this guy into this point. Okay, and that will give you what? That will give you this. Yep, this. That's the A. Okay, Q enclosed. Of course, this is a constant, so it comes out of the integral sign. That's a constant. And the A equals enclosed charge. Enclosed charge. And what will happen? I will divide both sides by this guy. This guy. So this will cancel now. Okay. So the next thing that will happen will be what? We'll have this guy. Okay. And that will give us this. what? Enclosed charge all over this. Correct. So these are in integral form. This is the first law. Okay, first equation in integral form. Right. Now we'll go to the next one. Alright, so this is the next one. Gauss's law of magnetism. Now, the net magnetic flux through a closed surface is zero, affirming that magnetic monopoles do not exist. That means the net magnetic, so also from this example where we drew this, so for magnetic flux, let's have it. Okay, so this is a closed surface. Okay, it's fair. So for the magnetic flux flowing through this, okay, magnetic flux going through this and the magnetic flux going out, they are the same. Okay, so in positive, out negative. So since in and out they are the same, they cancel out. Okay, they cancel out, meaning you have give you zero. And of course, the idea of magnetic monopoles, we've explained that in that video, saying that if you divide a magnet into two, a magnet has north and south. If you divide it into two, you also have north and south. Okay, so monopoles, magnetic monopoles do not exist. Simply means you cannot have one pole, meaning you cannot just have only north pole existing alone or south pole existing alone. No, there must be north and south together. Okay, so yeah, so how do we write that mathematically? Magnetic monopoles do not exist. Net flux has to do with the idea of what? Total, and then we'll come to our integral sign, bro. Net has to do with what? Total. Excuse me. Alright, so we'll come to our integral sign. Now, through a closed what? Surface. You see that sphere I drew there? So it's a closed surface. Okay? So, magnetic flux, isn't it? So this is how I write magnetic flux. And this integral is over the surface. So, surface area. Okay? Total surface area. So we use A for that. You can use S if you want. I will say it's equal to what? 0. This is it. Simple as that. Straightforward. Okay, so this is the third law. Okay, and the third law. Now, what we write here, like this third law, this is what it means. This, if you look at the integral form and the differential form, they mean the same thing. The difference is that one is for total, one is for just a point. I've said this over and over again. So this law just explains how it is in like total view. Then the other law talks about how it is for a particular point, but actually they are the same laws. Okay, the same laws. Okay, so a time varying magnetic flux. So a magnetic flux that changes with time. Let's put that magnetic flux. Okay, magnetic flux. So this time magnetic flux changes with what? Time. Changes with time. Okay, time varying magnetic flux through a surface. So we are taking surface integral, and of course it will be dA. Okay, so what happens to it? It induces a circulating electric field along the boundary. So it induces a what? Circulating electric field that circulates along what? The boundary, and the boundary has to be closed. So this is a line integral. Why do I say line integral? Look at, imagine this surface now. Okay, this is just a surface. Now if you look at the edge, the boundary is a line. The boundary is a what? It's a line, and it's a closed boundary, just like a ring. So that's why we have this closed. So what they are saying here is that this magnetic field that changes with time, this magnetic field that changes with time over the surface. Look at the surface, okay, over the surface, it induces an electric field along the line, okay, circulating electric field along the line, which is the same thing as along the boundary. Are we getting it now? So imagine this as a plate. If it's a plate, okay, or just flat surface, okay, so all the magnetic field in this surface, okay, induces what? The induces electric field, circulating electric field along the boundary. Now note that instead of using partial derivative here, I use just a single, like ordinary differential instead of using partial differential. Why? Because we are taking the integral, okay, we are taking the integral here. So, and also note that we said when we were doing a differential form, we said that this current, this electric field is opposite, it circulates opposite to the magnetic field, meaning we are going to have a minus sign here, just like in the previous one. So this can also be written when you just switch the sides. Take this one this way, take this one this way. It can also be written as, let me just copy the whole thing. It can also be written as, or let me just quickly read this. The L equals negative the T, that's big over okay, so this is what we have. All right, so for the fourth one and the last one in this video is this Maxwell's law. So the circulation of magnetic field around a loop results from both conduction current and time varying electric field. So circulation of what? Magnetic field. Circulation around the what? Loop. Around the loop, so circulation. Okay, so of course that's line integral. So this is as a result, that's for magnetic field. It's as a result from both conduction current. So for the conduction current, we have this, and it's what? The total conduction current. That's conduction current in enclosed surface. Okay, plus what? And conduction. So it results from both conduction current and time varying electric flux. So time varying, that means we have this time varying electric flux. Okay, time varying electric flux. Oh, that's correct. Electric flux should be D. Okay, electric flux should be D, but D equals this and then this. Is that not so? So that means since it results from both conduction current, this guy, and time varying electric flux, this guy, instead of writing D, we wrote E. So we have to write this guy also. So we have it here. Okay. Now, not only that, remember that there is permeability when we talk about magnetic flux. So we have to add that to each term. Permeability here, and then permeability here. Okay, permeability there. Then of course we have this here, integral there, dot what? Of the surface, okay, over a surface. So this should be dA. Okay, so let me just rearrange this to make it a bit neat. Make it a bit neat. Take this guy out. So this is just the whole idea. So let me just make this guy neat. By taking out the constants. The constants should be outside. this guy should be outside, and then we now the t, and then integral, surface integral, and then the a. Okay, so this is it. All right, so much, thank God. So yeah, we'll stop here in this video. These are the 4 equations in integral form. So of course, leave comment in the comment section, like, share, subscribe, and in the next video we'll talk about wave equation. Okay, so we've done this, and this, also this. So the next video we'll talk about the wave equation for electric field and then magnetic field. That will be true with this set of topics, these sets. Okay, so thanks for watching and bye for now.